Hi, my name's James Newton King. I'm an engineer with the ASP.NET Core team, and today I'm going to talk about high performance services with gRPC, in particular, what's new in .NET 6. So our agenda for today, first I'm going to give an introduction to gRPC for anyone who's not familiar with it, and we'll do a demo building your first gRPC app. Then we'll jump into what's new in .NET 6. So we've made performance improvements, we support transient fault handling, client-side load balancing with gRPC, and gRPC over HTTP3. Finally, if you're interested in learning more about gRPC, I'm going to cover some resources with more information at the end. So gRPC, it's a popular open source remote procedure call framework. RPC frameworks make it easy for apps to talk to each other. The gRPC project is run by the Cloud Native Computing Foundation, the CNCF, and what Microsoft has done is we've written a new implementation of gRPC for .NET that uses the latest and greatest features in .NET 5 and 6, and we've contributed it to the CNCF. So we're working together with them to make gRPC a great experience on .NET. gRPC is supported by every major programming language. So there are implementations for C++, Java, Go, Node, Ruby, Python, C#, you name it, there is an implementation of gRPC for it. And all of these implementations are interoperable. So you can have a Xbox game written in C++, have a gRPC client that calls a server that's running .NET 6. gRPC is contract first. So messages and methods are defined in a contract, and that contract then drives code generation via tooling. gRPC is not new. It was originally open sourced in 2015, but it's a union of two modern technologies, HTTP2 as the underlying protocol, and protobuf is the serialization technology for messages, and also acts as a language-independent contract format. And together, those things plus tooling equals gRPC. Fundamentally, gRPC is really just another way for apps to talk to each other. A client app calls the server with a request, and it gets a response. The first difference between how gRPC works and something like REST might work is with gRPC, HTTP2 is required. Also, rather than sending text-based JSON messages backwards and forwards, gRPC sends binary protobuf messages. The bigger difference with gRPC is how gRPC apps are written. It's contract first, with messages and services defined in proto files. This is a language-neutral way of defining the shape of your service. From this proto file, using tooling, a service-based type is generated for your server app, and a strongly typed client is generated for a client app. So how does gRPC compare against JSON and REST? No technology is strictly better than something else. There are always some trade-offs you need to balance. So the great thing about HTTP2 is it enables multiplexing. So multiplexing is where you send multiple requests simultaneously via a single connection. HTTP2 also means gRPC can do advanced streaming. So it's possible to stream multiple messages over a request to a server and then get multiple replies back. So you can talk with bidirectional streaming, which is a feature which just isn't possible using RESTful APIs. Protobuf is high performance, it's small, it's fast, it's optimized for computers to read and write. The downside with protobuf is it isn't human readable. So if you want to debug what's going on, if you want to view a protobuf message, you can't just open it up in a text editor like you can with JSON. You really need tooling, and tooling which knows about your proto file, or alternatively, you build a client app which has your proto file. And then finally, code generation. It's really great for productivity. Just by defining the shape of your service and your proto file, you get a whole bunch of code generated on your server, a whole bunch of code generated on your client. So out of the box, gRPC will generate a strongly typed client. You don't need to manually write it or add additional tooling after the fact. It's all just built into the gRPC ecosystem. The downside here is you need to learn about this proto syntax, and also you need to set up tooling. But fortunately, that's very easy to do with .NET. You just reference a NuGet package and you're good to go. So let's build our very first gRPC application using .NET. So what I'm going to do is I'm going to open Visual Studio and I'm going to create a new project. So there is a gRPC template which ships with .NET 6. So we just search for gRPC and this will create an ASP.NET Core website. So gRPC Server 79, that looks like a pretty good name to me. And we're going to choose .NET 6, long-term support, that's pretty exciting. And we'll click Create. So what's going to happen is the template's going to create a brand new ASP.NET Core app with gRPC already set up and ready to go. So what do we have here? The first thing you'll notice is we've got our standard program CS and app settings, but two new things that you won't typically see is we've got this greeter service and greet.proto. So greet.proto, this is the contract I talked about, and greeter service is an implementation of that proto file. So let's take a look at that proto file. So this is a language neutral syntax for defining what a gRPC service looks like. Here is where you define a service and the messages that you will use with that service. So we've got a greeter service with a say hello method. So you can think of a service like a controller in MVC, and then a method is like an action in MVC. So our say hello method is taking hello request, which has a name property, and it's returning hello reply, which has a message property. So this is hello world. We're sending a name to the server and we're getting back a reply, a message. So this is the contract. Our implementation is in the greeter service file, and it's just written in C#. So here we've got our type and we've got a say hello method that takes hello request as the incoming message and it returns hello reply. And here we can see in our implementation, we're just simply appending the name to hello. So pretty simple so far, but something which jumps out at me when I look at this is where are these types coming from? We've got greeter base, we've got hello request, hello reply. We haven't written these types anywhere. And the answer to that is code generation. If we navigate to the definition of our greeter base file, we can see we've got a whole bunch of generated code in this greet.grpc file. So this is living in a temporary object location. It's generated on the fly by tooling. And on greeter base, we have our say hello method, which is virtual by default. And its default implementation is to throw an unimplemented error. But what we've done in our greeter service is we've just simply overridden it. So likewise, our messages have also been code generated. So how does code generation work? If we take a look at the CS_proj file, we've got this protobuf element, which is referencing greet.proto, and then we're specifying we want server code generation. So we want that server space type rather than a strongly typed client, simply because we're writing a server. And that's pretty much all there is to it. So let me make one modification. I'll just make it so we log a bit more so we can see what's going on during our demo. And I'll compile this, just double check everything's working so far. Great. So now we need to call our service. Now, gRPC, it's not like REST where we can just open up a browser and browse to a URL with a get action and get some JSON back. You either need tooling, which knows about that proto file, or you create an app, which we're going to do right now. So what we'll do is we'll create a brand new app, a console app, which will act as our client. Click next a bunch of times. And now we've got our basic Hello World client app. Let's make it do Hello World to our gRPC service. Now, the first thing we need to do is we need to bring in our greet.proto file because both sides of both the client and the server need to know about the contract. And also we need to bring in tooling and some client libraries and serialization libraries. Now, I could do this manually by editing the CS_proj file. Fortunately, Visual Studio has this great feature called adding a service reference. So we're going to manage connected services. Then we'll choose add service reference, gRPC, and in this dialog, we will browse to our gRPC greet.proto file. So we're just browsing to this from our gRPC service 79. Click OK. And we want to select the type of code generation we want. So previously on the server, we saw server code generation. This is a client. We want the strongly typed client. So we'll choose client code generation. Click finish. and a bunch of things start happening. Visual Studio is adding some NuGet packages for us. It's adding the greet.proto file for us, and we're done. So all that did was just update the CS_proj file for us. So here are our NuGet packages, and importantly, here is our proto file with a client code generation selected and ready to go. So let me just compile this, double check everything is working. Oh, we got a failure. Oh, that's because I've taken everything out of the main method. So in our main method, we'll add a gRPC channel. So gRPC channel, you can think of a representation of a connection between the client and the server. So our client will specify the address of the server, and when any calls are made using this channel, it will go to this server address. And then this greet.greeter client, this is our strongly typed client. So this is what comes from code generation on the client. If I F12 into this, go to its definition, again, we'll see a whole bunch of code generation. It all looks pretty ugly and messy, but fortunately tooling is writing this, so you don't have to. And you can see up here, just confirmation that this is coming from greet.proto. Okay, so we've got our channel going to our server. We've got our client. Now let's use our client. So we're gonna get a reply from the server, and we'll call client.sayHelloAsync. So this was automatically created by code generation because we have that sayHello method in our contract. We'll send a hello request. It's a name property. We'll say hello.net conf, and we're done. So that's our call to our gRPC server, very simple. And let's write out a response. So we'll write from server reply, and let's write the message. So this is the reply from our server. And compile this, double check we're all good. And now we need to call it. So let's open a terminals. Let me get the path to our new project. We'll browse to this, and we'll browse over here. So we'll call both our, so we can see both our server and our client running simultaneously. So one last thing we need to do is our server has a slightly different port. So .NET Run on our server just started up Kestrel. gRPC is hosting Kestrel. You can host gRPC side by side other application types. So we're gonna just update our console app with the right port. And now if everything has gone to plan, we call .NET Run, we should see from server hello.NET Conf, and that's exactly what we see. So our .NET Conf name went off to the server, we got hello.NET Conf back, and here on the server we can see confirmation that it received it. So this is an incoming gRPC request. You notice it's using HTTP2, and it was successfully processed, and we can see here it was matched to a gRPC endpoint. So that's gRPC in a nutshell. As you can see, it's very simple to get started. The great thing about gRPC is it handles a lot of the lower level nuts and bolts. We never needed to worry about how to do serialization or routes or URLs or headers. Like all of that was generated for us. So gRPC plus its code generation can be a very productive experience. And not only is it productive, it's also very fast. So it's using high performance protobuf and HTTP2. Speaking of performance, that's a good segue into what we've added in .NET 6. So we did a lot of work on performance in .NET 5. We've just continued to improve in .NET 6. So in our serialization library, we now have a super fast path for serializing ASCII strings. So we've leveraged SIMD, so that's single instruction multiple data, to process characters in parallel using high performance CPU instructions. By doing that, we've measured a 20% overall performance improvement when serializing typical protobuf messages. Just from that string serialization taking up so much time, it's so much faster, 20% performance improvement is great. Another common use of gRPC is sending and receiving raw bytes using this type called byte string. So previously, when you were creating a byte string in your application, it always took a copy. So it always allocated a new array. and take a copy. And it did that because byte string, by design, it was meant to be immutable, so it takes a defensive copy. We've added a new helper method that allows you to bypass this extra work. It's called byte operations.unsafe_wrap. So if you know a byte array isn't going to be modified, you can use this type to avoid the extra work involved. Now, this is really important if you're working in an app which is sending and receiving large messages. You can save all those allocations and potentially reduce garbage collection and improve performance. gRPC download speeds are much faster when downloading large files and there's latency. So in .NET 5, we noticed that HTTP2 back pressure was limiting download speeds when there was latency. There was a fixed buffer size and it was just getting filled up too quickly. What we've done in .NET 6 is now the underlying HTTP2 library will detect if there's latency between the client and the server. And if there is, it will just automatically increase the buffer size. And that allows a faster continuous download speed. So this example I've given here, we've got a transatlantic 2 megabyte download from America to Europe. .NET 5, it took over 6 seconds. .NET 6, only 1.5 seconds. So significantly faster. We've heard a lot about Blazor ahead of time compilation. That also helps gRPC when run in Blazor. Because gRPC uses source code generation, it's able to take full advantage of ahead of time compilation. I've measured serializing 10,000 items in Blazor WebAssembly with gRPC takes just 3 milliseconds, which is ridiculously fast. That's the kind of serialization speed you'd typically see on a server with a high performance server and like fast runtime like .NET. But with Blazor WebAssembly and ahead of time compilation, you now have that similar performance characteristic inside a browser. So our next new feature, gRPC calls can be interrupted by transient faults. So transient faults can include things like loss of network connectivity, temporary unavailability of a service, or timeouts due to server load. If there's a transient fault, you don't want your gRPC call to fail. You want to be able to recover from it and provide a good experience to users of your app. So what you can do in .NET 6 now with gRPC client is you can configure it to automatically retry failed calls. So you configure the statuses, the error statuses you want to retry, how many times you want to retry, back off, exponential back off, things like that. And by centralizing this logic in gRPC client, you can avoid the need to duplicate transient fault handling throughout an app. So how does it work? It's quite simple. If you make a call and you get one of those failing statuses that have been selected to retry, the client will just automatically retry it. And it will keep doing that until it either gets a successful result or the number of retries allowed is exceeded and you get an error thrown back to your calling code. So the biggest new gRPC feature in .NET 6, and the one I'm most excited about, is client-side load balancing. So this feature allows a client to load balance RPC calls across multiple servers without requiring a proxy. Now, there are many reasons why proxies are useful, but there is a cost to using them. They add additional network hops, which adds CPU usage, memory usage, and latency overhead to your app. Now, if you can use client-side load balancing to eliminate the need to have a proxy at all, you can get significant performance improvements in your app and architecture. So how does it work? Earlier, when we created a gRPC channel, we specified a single address. When you're doing client-side load balancing, instead of specifying a single server, you'll specify the address you want to discover endpoints from. So the gRPC client supports endpoint discovery. In this example, I've configured a DNS discovery service. So what will happen when the gRPC client starts up is it will call off to the discovery service, and the DNS service will return a list of IP addresses, and those IP addresses are the servers that we're able to load balance across. So the gRPC client now, when making calls, when it makes them, it will select a load balancing policy. In this case, we've got round robin. We send requests to server 1, then the next request to server 2, and back again. So load balancing and with round robin is an example of distributing load. The client will also monitor connection health when this is enabled. If a connection to a server goes down, probably because the server itself is down, then requests are automatically load balanced to healthy endpoints. So if server 2 dies for some reason, then all our requests will now get all sent to server 1, because there's no point sending them to server 2, they're just going to fail. Additionally, when a server fails, the client is smart enough to start asking the discovery service, hey, have you got new servers for me? Have you got new endpoints that I should talk to because one of these has failed? And the discovery service will eventually say, yes, server 2 on address 101 is no longer available. Now talk to server 2 on 102. Now, if this scenario that I'm describing sounds familiar, it's basically what happens in Kubernetes. In Kubernetes, you've got a service which has a DNS endpoint you can query to get all the IP addresses of pod instances. And then if a pod instance dies, when it's recreated with a new address. So let's demo this using Kubernetes right now. So I've got a basic front-end app. So this is written using Blazor server, and we're just getting weather forecast data, and we're getting the weather forecast data from a back-end gRPC server. Now, if I click reload, it will reload the data, but you also notice this IP address. So this IP address is the IP address that we're getting this data from. And we've got two different IP addresses here. Down below this, I have got information about the available servers that we can call. So we're doing round robin, and then we've got these two IP addresses. And note that they're ready. So ready is a status where this endpoint is available, we can talk to it, and things are good. So if I go over to a Kubernetes dashboard, we're able to see the deployments. So we've got the front-end deployment for our Blazor server app, and then back-end for our gRPC servers. And you'll notice we've got pods 2 of 2. And if we look down here, we can see we've got our 2 pod instances. So we've got our front-end server and 2 back-end servers. Now, what happens if I kill one of these back-end servers? So we just killed that pod. And you'll notice in our client, we're now reporting that we're trying to connect to server 136, and that's because it's no longer available. And if we start reloading, you'll notice all our requests are now going to 135. So what our client is doing is it's attempting to reconnect to this endpoint, and then in the background, Kubernetes is spinning up a new pod instance, which will have a new IP address. And then the next time DNS updates, which just happened, now we've got a different address. So 36 is gone. Now we've got 37, and 37 has a status of ready. And now if we reload, we bounce between 35 and 37. We also support scaling up and down. So one of the great things about Kubernetes is you can quite easily scale it. So let's scale from 2 backends to 8. So now we've gone from 2 of 2 pods to 2 of 8. So Kubernetes is spinning up an additional 6 pods in the background. If we scroll down here, we've got a whole bunch more gRPC servers now available. We've still just got one front end though. And if we come look at our front end, we can see it's automatically reacted to that. So it's used service discovery. It's noticed that all these new endpoints are available. And if we click refresh, now our IP address is going across them all. And likewise, we can scale down. So scale, and let's go back down to 2. And these have all gone back to a connecting state. So I'm pretty excited about client-side load balancing. I think this is a capability that hasn't been really explored in the .NET ecosystem before, and I'm excited to see what people do with it. Final feature I'll talk about is HTTP3. So ASP.NET Core and HTTP Client support HTTP3 and .NET 6 as a preview feature. With gRPC, we're able to do end-to-end support over HTTP3 with gRPC calls. Now, this is quite interesting because the .NET gRPC implementation is the first one which supports this. And we've submitted a proposal about how to do it, and hopefully the rest of the gRPC ecosystem also starts supporting HTTP3. There's nothing really to demo here, but just talking about some of the benefits with HTTP3. First request is faster. improved performance when there's connection packet loss, and devices when they're moving between Wi-Fi and 5G, for example, there's a more smooth transition, like you don't kill a TCP connection and recreate it. So that's all I have to talk about today. I've got some resources here if you're interested in learning more. So there's a lot of topics I haven't covered, like how to version gRPC services, performance best practices. But if you're interested, check out docs.microsoft.com. And likewise, there are a lot of examples. Each example looks at one feature in depth. And if you're interested in learning like how to do streaming or cancellation, check out the gRPC repo, and you might see an example that shows you what to do. And that's it. And hopefully I've got some time for some questions.
Yeah, thank you so much, James. That was really cool. Okay. Oh my gosh, gRPC is just such an essential component to keeping .NET not only like on the cutting edge of services, but especially microservices and any kind of like multilingual app structure. So we play nice with other languages. Absolutely loved it. We got some questions here. So can we convert REST APIs to gRPC?
Well, there's nothing to automatically convert from one to the other. So I think the answer is not easily no. But if you want to make that investment, you certainly can. Like it will require additional work because generally with REST, JSON serializes the code is the contract, while with gRPC, the proto is the contract. So you'll need to recreate all your messages in protobuf. There's a bit of overhead and work. So I say certainly you can do it, but probably not with a snap of your fingers. It takes some work.
Okay, good to know it's possible. So just some praise, great work, super interesting demo of gRPC on .NET 6. And we have a question. Can Blazor WASM now use gRPC to send binary data to the server, or are we still restricted to text only?
Well, you've always been able to send binary data over gRPC Web. So gRPC Web, if you want to do server streaming, so that means the server streaming messages to the client, that requires some overhead of base64 encoding the content. But if you're not using that, then you can just use raw binary protobuf between the client and your server. And protobuf, it can be significantly smaller than JSON, so there's definite bandwidth performance improvements there. And also, if you're choosing to send raw binary, with JSON, there's no way to like send raw binary. You have to send it as text, which means you need to base64 encode it. Protobuf and gRPC is interesting because if you want to send raw binary, you can send it directly without the overhead of base64 encoding, which is, I believe, like a 30% overhead, which is something you can avoid.